Alright, so I've done some correction work on and some more fleshing out of this batch notation. So here we have pretty much an outline of how it works now. Right, so you've got your curly brackets. The first item indicates your reference frame, and then you can get auxiliary conditions, and then after that you can get your commutative batch terms. And then this whole thing will be equal to some function name with input values. So in a lot of ways this is very similar to how like a C or C++ function looks. Very similar to that. And it kind of works similarly, but there's a lot of differences too. And the output is the reference frame modified by the batch terms. Okay, so these auxiliary conditions can control how the batch terms are modifying the reference frame, but the output is just whatever this does to this. I probably don't have that 100% consistent in my definitions. Yeah, so I've added logical relations. So the comma is and, that's always been the case. And then an apostrophe is or, so it's like a comma but higher. This is inverse, so this is a built-in part of the language, right? The negative is the inverse or the negative or logical not. Okay. Expression comparators, so you have equality, inequality, optional in, equality, inequality, optional in, equality. Assignment or definition. This one, I think this is from like Algol or Fortran or something. Yeah, I'm just using it because it has historical precedence. And then other stuff that we've seen before. Okay, so here, most of this we've seen before, but I wanted to derive the plus, the multiplier, and the division, and the caret, and I think I have it here, yeah, the root. I wanted to derive all of those from the language itself. So I realized the easiest way to do that was to drop in a step between existentiation and incrementation where we take the measurable existence or the dimensional unit and we actually compose it with non-existence in such a way that we get a specified direction. So basically we're establishing our working dimension. So we're taking kind of out of any random dimension, we're pulling this unit. But then what we're doing is we're dropping it onto our working dimension, like basically our workspace. And the way that we're doing that is we are using the negation to establish direction. And then we negate that to get the positive. So the positive one is more derived than negative 1. And this is the third time that I have unintentionally derived the conclusion that negative 1 is more basic than positive 1. So I think it's just true. This is the third time I've done it in the third completely different way for a completely different reason, and I wasn't seeking to come to this conclusion any of the times. So I think it's actually just true. Right? And then I've cleaned up, the way this kind of modernized it, with I think the last time I showed this, it didn't even have the dot here to indicate that this is the number of iterations. Yeah, so I've cleaned it up. I've I've figured out the philosophy behind the way that it works and how all of the parts should work now. Just kind of like following it, just playing with it and trying things and letting it tell me where it should go. So this, yeah, so now I have multiplication specified as iterated addition. Being an idiot, I didn't have that in the first place. I wasn't all that interested in establishing this correctly the first time around. I was more interested in doing this correctly, and I did, but I didn't do multiplication correctly. So there's all of these things are the same as each other. So what this is the more basic. So this is taking this established addition here and turning that into multiplication and defining the star via that. Just as here, double negation is the positive, iterated addition is the multiplication, negative multiplication is division, iterated multiplication is exponents, iterated division is negative exponents, so these are the negative of each other. So again, this holds, so the negative of multiplication is division. That's what this negative is meaning. And if we're taking the 1/2 power of something, we're getting the square root of it. Alright, nothing groundbreaking, but now it's all formally there. Calculus, I don't think I touched those since we last saw them. If you want to look at them again, I'll leave them on screen for half a second longer. So there's integrals, definite integrals, derivatives, limits. Reasonable classes. So properly, numbers, magnitudes, unit vectors, infinitesimals, measurables, and m vectors, which would roughly, the measurables actually more closely resemble the reals, but the claim that the reals are continuous is most analogous to this one, because these are properly continuous. And then the curl vectors, which are like my analog to the imaginaries, except that they are these guys multiplied by root negative 1, which means in general it's not defined what they are. There's around one m vector space you're going to get a ring of curl vectors, or curl vector spaces, and that's not the like group theory sense of a ring. It's not that. It's like a literal circle. Okay, the classical ones, not so interested in those. And a library of functions, basically. So, and I've listed, I have them in order of which ones can come first. So we can find fractional parts of a random vector, k. So this is an important thing because I was invoking that before. It took me a minute to figure out how to do this exactly. So that one, it requires the addition to be specified. Technically, I guess it doesn't, but it's simpler if we use it, if we define addition first, or the positive first. This one, yeah, the numbers and incrementation, they pretty much go hand in hand. They're sort of like, they create each other, basically. So this is defined by incrementation instead of, like, this is defined after the positive. This is defined by incrementation, and doing the numbers defines incrementation. So there's that. And then these are defined after that, so you can get the Fibonacci sequence. So there's the algorithm for that. And then after we get plication, So that's multiplication and division. We can take factorials. So all of this stuff here, what this is doing, this is setting up the context so that when we do this operation, it works correctly. So this is actually operating very much like a computer program. So here, and we can even run basically computer programs in here. So Mandelbrot set, what this is doing is it's determining membership to I iterations of complex vector C, right? So you're inputting the complex vector C with the M vector and the curl vector, and you're also entering the number of iterations that we're going to compute this to. And what the output of this is going to be is the number of iterations that we reached. So if the output is the same as the input, what it means is we couldn't determine whether it's in the set or not. As far as we can tell, it looks like it is. But if the output is less than the number of iterations, then it's definitely not in the set. Okay, this is a pretty standard way to write this. So you would color code the options, and that's how you get those nice pretty pictures. The Julia set is very closely related to the Mandelbrot set. So if we can do the Mandelbrot set, we can do the Julia set. And then here is for computing the fundamental circle constant. This is that little, it's really the Python program that I have that does this. I just converted it to this notation, and then once we have exponentiation defined, we can define complex vectors. So I guess technically this should occur before that. This should be, like I said, there's probably errors in here because I'm doing it all in my head. Like I can't like run it through a computer and test it. And I'm also just doing it in my random free time. So there's that. And then old stuff. Yeah, so there's curl infinitesimals, curl vectors, etc. All that. Curl measurables, curl units. Yep, that's pretty much where we're at right now. As you can see, I'm still editing even as I'm talking about it. So it continues to be a work in progress. But some interesting results. Positive 1 is more derived than negative 1. Note that under the Peano axioms, natural number 1 and positive 1 are the same thing. That is not at all the case here. Not at all. Here our number 1 is dimensionless. It's just a norm. Whereas positive 1 is a unit vector. Very different things. And negative 1 comes before positive 1 when we're deriving things. And like I said, this is the third distinct way that I've come to this conclusion. And I've never sought to come to this conclusion. So I'm pretty sure it's actually just true. Because I've come to this conclusion multiple different ways without ever seeking to come to this conclusion. So it's probably just true.